the end of trigonometry. So like,
Oh, it was my turn.
we can say goodbye to sine, cosine, and tangent, unless you're taking the final. So the pre-calculus section of this class is going to be largely review and extension of topics we've seen either in Algebra 1 or Algebra 2. So that's nice that most everything here that we're going to be seeing is going to be familiar. And that familiarity is going to start today in section, or in this supplement A. We're going to be talking about solving systems of equations. So when we talk about a system of equations, we need to specify the number of equations and the type of equation that we have. So here we're going to be looking at two linear equations. So 2 is the number and linear is the type. So two linear equations might be something like in the form ax plus by equals c, and then dx plus ey equals f, where a, b, c, d, e, and f are just like real numbered constants. We say that a given value is a solution to a system of two equations if that xy satisfies the first equation and it satisfies the second equation. So one way that we can kind of think about solving something like this is thinking about it from a graphical perspective, right? If equation 1 is a graph, it's linear, so it's just a straight line. And equation 2, if I think about that as a graph, it's also a straight line. So any xy that satisfies equation 1 has to be on the line formed by equation 1. And any xy that satisfies equation 2 has to be on the line for equation 2. So if that xy satisfies both equations at the same time, it has to be on the intersection of the two lines. So that kind of reasoning is our motivation for our first method that we're going to look at on how to solve something like this. So let's take an example. So to graph this, I'm going to start with equation 1, and I'm going to rearrange that so that it's in slope-intercept form. So I want it to look like y equals mx plus b. Basically, I just want to make sure the y is all by itself. So what do I need to do to this first equation to get y by itself? Shame on every single one of you. This is an pre-algebra 1 question. Yeah, subtract 4x from both sides. Very good. And now it's in the slope-intercept form, right? To graph a line, what do I need to do? How many points do I need to graph a line? How many? 2 is enough. 3 is fine, but 2 is sufficient. So I'm going to pick a value for x and find the corresponding value for y by plugging it into the equation above. So if I pick 0 for x, what should y be? Again, this is like some pre-algebra here that we're asking. If I plug 0 in for x, what does y have to be? So what does y have to be if I plug 0 in for x? Not negative 4.
0.
Not 0.
Oh, 0 plus 8.
which is just 8. There you go. Good. And let's pick another value for x. Maybe I'll pick 2 this time. What does y got to be then?
16.
Nope.
Negative 16.
Nope.
Oh. Oh. 8. 0, 0. No, negative
0. Negative 8 plus 8 is 0. We're refreshing, right? All right, let's look at the next equation, 2. So again, I want to start by getting the y by itself. First thing I should do is?
divide the 3.
No.
Minus the 2x.
Yes.
Then you divide the
Good. And really, I'm going to divide by negative 3, though, right? So the negatives cancel out. And what's 18 divided by negative 3?
6.
Close, negative 6. And we'll do the same thing. What x's should we pick?
0.
0 sounds good. What is y then?
Negative 6.
Great. What's another x to pick?
1.
Let's pick, yeah, let's not pick 1 because we're going to end up with stinky fractions.
Let's go 2.
2 will still give me stinky fractions.
Let's go.
I want my x to be a multiple of 3 so that when I multiply by 2/3, the denominator cancels out.
9.
I'll just use 3. That seems simpler.
Okay.
9 would be good, though. That'd be good. It's just a lot of tick marks to make when it's time to graph. When I plug 3 in for x, what do I get? What's 2/3 times 3? Not 6/9. So how do you multiply fractions? Straight across, right? What are the two fractions we're multiplying? 2/3 and 3/1. Right, because we're plugging 3 in for x. So 2/3 times 3/1 is,
6/3.
which is, and then minus 6 is, there you go. All right, so now let's try to draw our graph. So 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1, 2, 3, 4, 5, 6. And then 1, 2, 3. So I'll do my red one first. So I have 0, 8. And then 2, 0. Everybody feel okay with that? Grab my ruler then. Okay, that seems about right. Draw my line. And then we'll draw my blue one, so 0, -6. And then 3, -4. 1, 2, 3, 4. And grab my ruler. And draw my line. And what does it appear that my solution is? Looks like that, right? What's that point? Can we read that? 1, 2, 3, 4. About 3, negative 4. Everybody's okay with that? Let's check now. So I'm going to take equation 1, which was 4x plus y equals 8. And I'm going to plug in my x and plug in my y. What's 4 times 3? It's taken way too long. What's 4 times? There you go. And then minus 4 is?
8.
That one worked. Let's now check equation 2. So that's 2 times x or minus, 3 times y equals 18. So my x was still 3 and my y is still negative 4. 2 times 3 is?
6.
Negative 3 times negative 4 is?
12.
6 plus 12 is? That checks out. Everybody good there? All right. So that we've seen this, how this method works. Everybody okay? What's the downside here? What's the downside? You gotta make a graph, right? And really, what's the problem with having to make the graph? Give me some downsides. We just did it. What parts didn't you like having to do? Okay, you have to make a table to generate points, right? How much space did it take up on your sheet of paper? It's kind of a lot of space, right? When you drew your graph, did you get it to line up exactly at 3, negative 4? Or was it just kind of like in the area? How are you going to get it to be, how do you, so let's say that the answer was actually like 2.9, negative 4.1. Is that going to be easy to get with the graph? No, why not? Well, it means that you're going to have tick marks up to the 10th, right? So you get down to negative 4, you're going to need 40 tick marks on your graph. Like, that stinks, right? Imagine if the real answer was in the 100th place instead of the 10th place. Like, you can see that this is going to be like really tedious. And how much neatness is going to count. So one workaround that we have when neatness counts, especially for graphing, is our calculator can handle this. So if you have your graphing calculator with you, I invite you to take it out and follow along. We'll run through how to do the exact same process here with our calculator. Because your calculator has no issues with neatness, right? Your calculator says, I can be as neat as I have decimal places for. You guys good? All right. So I'm going to start by pressing the y equals button. That's the one in the upper left-hand corner. And I'm going to write in the slope-intercept version for equation 1, and then the slope-intercept version for equation 2. So negative 4x plus 8. And then 2/3 x minus 6. Notice I don't have to type the y equals because, well, the y is already right there on my calculator screen, right? It says y equals. I just have to fill in the. Is everybody good? Now, I don't remember the last time I graphed anything on my calculator, so to graph this, I'm going to press zoom. And then pick option 6 that says Z standard. That's just going to reset my window back to the standard negative 10 to 10 range. And there's my graph. Looks just like what I did down here, right? Everybody agree? Now the calculator can actually tell you what that intersection is also. Let's show you how to do that. To get the calculator to do this for you, you're going to press the second button, that's the blue one, and then the trace button, which is up there on the home row. The commands in this menu are all things that you do to a graph. Which one of the commands listed here sounds like the one that we want? Intersect, right? Because we're interested in finding the intersection of the two lines. That's correct. So let's pick command 5 for intersect. And now look at the bottom of your screen. Your calculator is going to ask you a series of questions where it needs to know, okay, you want me to find an intersection. Great. What two things am I looking for the intersection of? So it's asking, what's the first curve? Notice my cursor is flashing here on this line. Well, I'm going to press enter. Notice that it automatically toggles my cursor down onto the second line. Then says second curve. So that's the other line I want to find the intersection of. I'm going to press enter. And then it asks for a guess. But how many times are these two lines going to intersect? How many times can the two lines intersect? Just once, right? So the guess doesn't matter if there's only one intersection. It's just the only thing it's going to find is the one. If you had something that crossed like a bunch of times, you'd want to make sure you were close to the intersection you're looking for. So so you find the one that you want. But in the case of these linear equations where there can be one intersection at most, just doesn't really even matter the guess. So I'll just press enter again. And it spits out the intersection is 3, -4. Done. Everybody okay there? All right. So if we continue to think about this graphically, we've seen that we can get one solution, right? Where the two lines intersect one time. What else could happen if we think about graphing two lines? Get like one solution. What else can happen?
Straight line. I was thinking like they're overlapping.
Yeah, great. So the two can coincide. How many solutions is that going to be? Infinitely many, right? Any solution on this line is a solution on that line. So you have infinitely many. Great. And there's one other thing that can happen. So you have intersection, coinciding, or overlapping. What's the third thing that can happen? Parallel. How many solutions do you have for that? 0, because they never overlap. Wonderful. Now you're warmed up using our noodles here. Okay. Now, so that's what the graphs would look like, right? Would it be nice to be able to look at our equations and tell which one of these three situations we were in before we even start the problem? Yeah, right? So for exactly one solution, if the slopes are different for our two equations, we're guaranteed one solution. Right? If we go back and look at our problem back here, one slope was -4, the other slope was 2/3. Since those are different, we know there's one solution, point blank and period. Everybody's good? If we have infinitely many solutions, if the two lines are overlapping, they have to be the same line, right? So they have to have the same slope and the same y-intercept. Is everybody okay with that? Should be really obvious when you get them into slope-intercept form. That's like, those are the same thing. You might have to reduce a fraction, but woo! We think we can handle that most of the time. If they're parallel, we remember from geometry, lines that are parallel have the same slope, but we don't want them to overlap, so their y-intercepts have to be different, right? That one's -4, and that one's like positive, or -1 and +6. Is everybody cool with that? So I can literally tell before graphing anything which one of these three situations I'm in. Is everybody cool with that? Now, the only one that would really require me to actually graph the thing is if there's one solution, because I have to specify the x, y. But in the other two cases, I mean, looking at the equations is good enough. I don't have to graph boo diddly. All right, let's look at an example to just kind of drive this idea home. Okay. So just like before, we're going to start with equation 1. And we're going to write that in slope-intercept form. What do I need to do first to get into slope-intercept form? Great. And I'm going to do that by subtract 4x from both sides. Let's write it this way. And then divide by -3. So the two negatives cancel there. But I have only one negative there, so I'm just going to change that to minus. Is everybody good? Okay. Now let's do equation 2. What am I going to do first here? So, good. And then we will? Good. So negative and negative make positive. And negative or positive and negative make negative. Did you notice anything going on with that second equation? What's up? Yeah, we can simplify that. We can reduce those fractions. What does 8/6 reduce to? 4/3. And what does 16/6 reduce to? Yeah, -8/3. And what do we notice here? So what does that tell me? Infinitely many solutions. I use that abbreviation IMS because there's a lot of letters in infinitely many solutions, and I'm not about that brevity thing. Feel free to use that abbreviation as well. What do you guys think? Notice I didn't actually have to graph anything here, right? I just looked at the equations and saw, they're the same thing. I'm done. All I have to do is state infinitely many solutions, and I'm on my way. Anytime I don't have to draw a graph, I'm a happy camper, right? Because the graph's just kind of a hassle. It's just kind of a hassle. All right. What do you guys think? It's all right? Okay. What if we, instead of talking about systems of linear equations, what if we talk about a system of linear inequalities? You remember what an inequality is? It's got like the less than or equal to and stuff like that in there. So here, even if I have two variables, I can have as many inequalities as I want, right? I don't have to have two like I do for the for equations. For inequalities, I could have 2, I could have 3, I could have 4, I could have 5, I could have 26. It doesn't really matter. You're not going to have 26. And almost every system of linear inequality or system of inequalities is going to be either infinitely many solutions or no solution. Well, Mr. Kulik, that's pretty dumb. Couldn't I just like IMS like almost all of these? Here's the thing. We're going to want to be specific about where those infinitely many solutions lie, right? Because infinitely many solutions doesn't mean that everything is an answer. It just means the answers that there are, there's infinitely many of them, right? So the way that we're going to do this is going to be as follows. What we're going to do is we are going to start by writing our inequalities into slope-intercept form. Now keep in mind when we do that, if we have to divide by a negative or multiply by a negative, what do we have to do? You have to switch the inequality symbol, right? Less thans turn into greater thans and greater thans turn into less thans. You guys remember that? Then we're going to pretend our inequality is a line, plot the line. So when we draw the line, we're going to use a solid for or equal to inequalities and a dashed line for strictly greater than or less thans. And then we're going to shade above that line if it's greater than or equal to, and below the line if it's less than or equal to. And look at the overlap of those shaded regions, because that's going to give us our solution. So let's look at an example or two of doing this. All right, first step would be to get these into slope-intercept form. What do you notice? They're already in slope-intercept form, right? The y's are by themselves. Oh, goody. So I'm just going to pretend that this is an equation, and I'm going to find 2 points on that line. What values of x do you want to pick? How about 0 first? I like that one. So I get -5. And then which one do you want to do? I want to do -1. The reason I want to do -1 and not +1, it doesn't really matter. 1 is fine. But if I do 1, I'm going to get -7. That's a lot of tick marks down to get to -7. If I do -1, I'll get -3. I've already drawn the 3 tick marks when I drew the 5 tick marks. I'm going to be lazy and do it that way. You guys cool with that? Now, what type of line am I drawing here? Should it be solid or dashed? Good. Yeah, if it's not or equal to, it's dashed, and it should be shading above or below? Above, because it's greater than. Okay, so same kind of thing here. So maybe I do that. Should equation 2 be solid or dashed? Solid, very good, because it's an or equal to. And should we be shading above or below? Below, because it's a less than. Everybody feel okay so far? Okay, let's draw our lines here. So 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3. Okay, so 0, -5. And then -1, -3. Okay, and this was a dashy. Ah. Stupid thing. Okay. And then my other one was 3, 0, and then negative 3, 0. Okay. This one was solid. So far, so good. Now we're shading above the red. So like that. And we're shading below the blue. So like that, right? Is everybody okay? So where's my solution at? It's the stuff in here. What do you guys think? So to check this, we can pick a point from that blue highlighted region. Maybe I'll pick 0, 0. And make sure that 0, 0 satisfies my inequality. So if I do equation 1, 0 should be greater than negative 2 times 0 minus 5. So is 0 greater than negative 5? Yeah. If I do the same thing, I should have 0 is less than or equal to 0 plus 3. Well, is 0 less than or equal to 3? Yeah. So there's my check. Is that check flawless? No, sir. But it's decent. What do you guys think? So again, like infinitely many solutions, like that's a solution, that's a solution, that's a solution. Is this a solution though? If it's on the dashed red line? No. Is it a solution if it's on the solid blue line? Yes. Everybody's cool? Okay, let's do one more and we'll call that probably good enough. This isn't too bad, right? Hopefully we remember kind of doing this. And let's do this one. Notice here that we have 3 equations this time. Oh my gosh. But the good news is they're all in slope-intercept form already. That's nice. So the first one, our xy, would be, let's do 0, negative 5, and then like 2, and that would be negative 1. This should be dashed, and we should be shading below. Is it okay that I'm kind of speeding through some of these now? So same idea here. We'll do 0, 8, and maybe 3, negative 1. This is solid and above. So maybe that's 0, 2, and then maybe we'll do 4, 0. And this is solid and below. Any questions on how I came up with any of that? I know I just buzzed through it pretty quickly, but you guys seemed okay with what we were doing. If you have questions, though, like chime in, dude. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. And then 2, 3, 4. Okay, 1, 2, 3, 4, 5. All right, so we have -5, and then 2, -1. Get my ruler out. It's probably pretty close. Ugh. My OneNote is being really kind of a pain in the tuchus today. And it's making me want to pick my computer up and just kind of like throw it out the window. You ever feel that way about yours? Yeah, I know I should have like better patience than that, but I just a lot of the times can't muster it. Whatever, that's probably fine. Blue, so now we have 0, 8, and then 3, -1. Okay, that's probably enough. Solid line. Okay. Oops. Ruler go away. Then 0, 2, and 4, 0. Draw that. All right, get that out of there. So for the blue line, red line, we're doing below. So we have to be like there. For the blue line, we're above. Ugh, come on now. And the yellow line, we're below. I don't know why it does this. All right. So where are all 3 colors being drawn? Right in there, right? So like that's my region. What do you guys think? It's all right. We're showing you that we can do these problems on our calculator. Also, although the picture can sometimes get a little bit hairy. So I'm just going to go ahead and type these into Y1, Y2, and Y3. So I did that. Now the dashed is or the red equation is shade above, right? So I'm going to move my cursor over here to the left of the y1. And right now it's set to be a solid line. I'm going to cycle through until I see the shade below. See how it's a full thing underneath? That shade below. I'm going to set this one to be shade above. Oops, pressed too many enters. So I'm just pressing enter to cycle through these. And I'm going to set this one to be shade above. Oops, I meant below. Everybody's cool with how I set that up? If I hit graph now, there's the red line shaded below, the blue line shade above, and the yellow line shade below. So our triple intersection is like this region right in here. I bet you think it's pretty cool that your calculator can do that. Did you know it could do that before? That's pretty neat, right? All right. So at this point, we've looked at these graphical methods, right? Now, we've already talked about why sometimes the graphical methods are el stinko, because, well, they take up a lot of space. They're relatively time-consuming. And then, like, neatness counts. That's kind of a trifecta of give me something else. Well, there are algebraic methods. Does anybody remember any of the two algebraic methods for solving a system of equations? There's two names. One starts with an S, the other with an E. Substitution was the S one. For a substitution problem, you want to solve one of the two variables, so get one of the two variables by itself. Using that new equation, I'm going to substitute in the right-hand side of my new equation into the other equation. That means I'll have an equation with one variable. I can solve that now using Algebra 1 methods, get a solution, and then plug that back in to find the other. So the first question is, which variable in which equation should I get by itself? Now, there's no wrong answer here, but there is a best answer here. So take a look at these two equations in our example. Which variable from which equation would be the one that Mr. Kulik would pick to get by itself? And then what variable?
X.
Excellent. That's what I would pick as well. Why? Because it already has a coefficient of 1. That means no division, which means no fractions. My goal here in the beginning is, if I can do this problem without having to generate any fractions, I want to do that. Not that fractions are a problem, but they slow everything down, right? We can deal with them, but if I don't have to, let's not. So to get the x by itself from equation 2, what do I have to do? Subtract 3y from both sides, right? Now what I'm going to do is in equation 1, I'm going to replace the x with what I know x has to equal. Can everybody see what we did there? Notice now I have only one kind of variable, right? Just y's. That we can solve for y, so I'll just distribute my 2 through. I'll combine some like terms. And then subtract 6 from both sides. and then divide by a -1. There's half of my answer. There's y. Everybody feel okay there? To get x, all I need to do is plug in y equals 11 into any of my previous equations that have both x and y. The one that I'm going to pick is this one, because the x is already by itself, so I don't even have to do any algebra. So my answer here is x is -30, and then y is 11. Done. Mr. Kulik, that seems simpler than graphing. Well, maybe not simpler, but less time-consuming and less neatness and oriented. Because look at the size of this one. Are you going to enjoy having to extend your graph off so far to the left that you can get to -30? I would not want to do that. Looks like a colossal pain in the tuchus to me. What do you guys think? So far, so good? Okay, let's remember what you guys remember doing this, I hope, right? In Algebra 1 and 2. I think you do it in both classes. We should be pretty good at this, or at least we're pretty familiar with it anyways, even if we're not good at it anymore. You should remember having remembered doing it and could get good at it again relatively quickly, because you surely were asked to be pretty good at it at one point. To do elimination, the goal is to make one of the variables have the exact same coefficients, or I should say opposite coefficients. So like I'd want x to be 2 in equation 1 and then -2 in equation 2, and then add the two equations, which is going to cancel the x's out. The resulting equation is one variable. I solve for the one remaining variable and then plug that answer back into any two variable equation to solve for the other. So my first order of business when I look at an elimination problem is to figure out which variable do I want to eliminate, x or y. So let's look at our two variables, x and y. Which one is Mr. Kulik going to choose to eliminate? Because I think one of them is slightly more convenient than the other. I'm not going to do substitution. We're trying to do elimination here. You could still do substitution here. But let's do this one by elimination. Which variable is Mr. Kulik going to choose to eliminate, x or y? I would choose x. The reason is to make the coefficients for x be opposite, I only need to change equation 1. How am I going to turn 3 into -6? I'm going to multiply the entire equation by -2. Now, if I tried to do the same thing for the y's, I'd have to multiply both equations by something, right? Equation 1 would have to get multiplied by like -8, and equation 2 by +7. And now the numbers have gotten quite big. I had to do 2 sets of multiplication, just that much more opportunity to make another mistake. Did you guys kind of see that? Now, it's not wrong to do the y's first. You'll still get the same answer. It doesn't matter which one you do. But again, try to look for ways to make your life simpler, right? Let's decrease the opportunities we have to make a mistake. So when I add these down, the x's cancel. 14y plus negative 8y is 6y, and negative 20 plus 8 is negative 12. So to solve for y, just divide by 6, and I get y equals negative 2. That's half my answer, right? What I'm going to do now is I'm going to take that equation and plug it back into equation 1 or equation 2. I'm going to plug it back into equation 1 because, I don't know, the coefficients look a little bit smaller in that one than the other. It doesn't really matter. So again, I'm taking the y and plugging in the negative 2. So I'll subtract 14 from both sides and then divide by 3. So that's the other half of my answer. So I'll say 4/3, comma, negative 2 is the whole shebang. There's one fine point to still talk about, because I don't always have to get a solution, right? What else can happen? I can get no solution, or I can get infinitely many solutions, right? So in my substitution problem, say I have x equals something, right? I just got that x by itself. So I have like 2 times that something plus like 3y equals 10 or something. Let's say we have this. If, when I simplify this down, the y's cancel out, and I get something like 0 is equal to 6, that tells me there's no solution. If I had gotten something like 6 is equal to 6, that tells me there's infinitely many solutions. Is everybody okay with that? So after you plug the one equation into the other, and you try to solve for the variable, all the variables are going to disappear, which is fine. If you're left with a true statement like 6 equals 6 or 5 equals 5 or 0 equals 0 or whatever, that's infinitely many solutions. If you're left with a false statement like 0 equals 1 or 9 equals 6 or 15 equals 4/3, that's no solution. In elimination, if I've added equation 1 and equation 2, and I get something like 0 plus 0 equals 0, that's infinitely many solutions. Or if I got like 0 plus 0 equals 4, that's no solution, right? Same idea. One is a true statement, that's infinitely many. The other is a false statement, that's no solution. So it always occurs after you've try to eliminate one variable. Oops, I eliminate both variables. That's okay. You just have to look at what's left and see, oh, did I get 0 equals 0 or did I get like 0 equals 10? One is infinitely many, the other is no solution. How are you guys feeling? This look familiar? Hopefully you're like, yeah, I can do this stuff. So at this point, you guys should be able to do up to 18. We're going to stop here. So 1 through 18, and this should be done for Sunday. Okie doke, artichokes. Okay.